Hello, and thank you everyone for joining today. So as said, I'm Pierre, I work at Swiss3, and I'm also a writer about the data space, and I'm going to do this sort of projects on the side. Yes, can you hear me? Yeah, okay. Yeah, so and then apart from that, you can see I've collaborated with different companies and wrote articles, like for example with NVIDIA, and some articles also being published by Cornell for their courses, or by Kaggle for sharing online, say. And so, yeah, starting with the topic, we are talking about paradoxes today, and paradoxes are, to give an intro, are a class of phenomena that arise when, although starting from knowledge is not true, we derive some sort of logically unreasonable results. And nowadays, machine learning models, they are completely based on data, and they make inference on data, and therefore, if there are differences, for example, between the training and testing data, they can also be suffered like we do with a bit of cognitive paradoxes, basically. And one of the main techniques that can be used to try to understand more of these paradoxes are, for example, modeling and simulations. And for understanding models, it's really important to remember that this quote from George Box, where it says that essentially all models are wrong, but some of them are useful, which is really important because models are always a representation of the real world environment, but they can never be one-to-one with the real world environment. And therefore, there are always assumptions or changes that they may not be able to capture over time. And it's important to know now, basically, that as for this first paradox, one of the main reasons why we use models, which are not really necessary to machine learning models or deep learning models like they are today, is that we want to basically understand an environment and make predictions on that. That's why data science was developed, let's say. But at the same time, in not all the cases, we have data to start with. And if we don't have data, how can we perform data science? And one way to do this is basically to generate this data through simulations. And this can be much more common than we normally think. For example, if we consider a thought experiment and we say, okay, we are a data scientist and we're working for a local authority, and we're asked to create a way to try to optimize an evacuation plan for a city in case there is a natural catastrophe, like earthquake, volcano eruptions, and so on. Hopefully these things don't happen so often, so we don't have data about how to model this sort of situation. And therefore, what we do in this kind of situation is try to basically create a synthetic environment in which we model the situation, the people, the escape routes, and so on, and run simulations against them and generate data, which can then give us results on how to then make best decisions and generate policies from the government point of view. And this was also done, for example, during COVID. In fact, if you remember at the beginning of the pandemic, there was no data, no people knew how fast it was spreading, what was the cause of spreading, and the disease, and so on. And in order to perform this sort of analysis, there are two main approaches. One is mathematical models, and the other is process models. With mathematical models, we generate a set of equations and that summarize the relationship between different states, and then run them and generate some results. Instead, with the process models, we handcraft the steps of the algorithm and the environment in order to then synthetically generate the results. And this can be used, for example, in for many situations. For example, one of the most basic ones that we might know are related to Bayesian inference, where you can have priors for the environment, or Monte Carlo simulations for portfolio optimizations, or things like that. These are all sorts of simulation techniques. And more complicated ones that are used nowadays, for example, relate more to, like, for example, doctor medical training in synthetic environments, or military operations in synthetic environments, and also epidemics and model threats for cybersecurity as well. And then, for example, once we got this data, you can then help governments or decision makers to basically experiment policies before actually apply them in the real world. So, for example, you could create a model to simulate COVID spreading, and you can see, okay, if I do a lockdown, what would be the results, how many deaths you expect less, and so on, before making an actual decision. And because these models are made and are crafted by us either through mathematical equations or through elaborations of steps in like algebra-based modeling, then that makes them basically a sort of a white box-based approach compared to using just heavy models for deep learning and to solve a solution, let's say. And so starting with convolutional models, as I said, they are based on equations. So you can see basically we can design, for example, 3 sets of equations here for modeling epidemics development. And in this case, we see we have 3 equations, differential equations that runs against time, where we can run a simulation. And the first one can represent, for example, delta S, the people that are susceptible to a disease. The second one, the people that are infected. And the third one is the people that recover from it. And then you can see that there are different parameters that determines how people can move between different compartments. And each equation can then be represented by a compartment in a diagram, where we can see then how the flow of the people can move throughout the simulations, and what kind of probability there is between a person moving between one state and another, at what rate people are moving, if it's a fast rate or a slower rate, and so on. And once we run this against time, then we can see you get these sort of curves and analysis, which are also, for example, been shown during COVID by many governments. For example, the UK government started with the Imperial Research Study, started with a much more advanced version of analytical model like the SIR, and during conferences, during lockdowns and so on, they were showing actually these curves to show how their policies were trying to bring down the orange curve in this case, and basically bring down the infected, the green curve, and then try to reduce the amount of people that would be suffering for that, let's say, and calculating the R value that you think can be estimated also through these simulations. Okay, really close, okay. Yeah, no problem. And yes, so the second approach is that I was mentioning about is agent-based models. And in this case, basically, we take sort of object-oriented programming approach where we create a class representing a person in the environment, and then give it different properties and parameters that can be played with. For example, you can obviously a position, a speed in which it moves, a direction, a certain age, how many, for example, days of rehabilitation has been going through after getting the disease, and so on. And then once run this approach, you can see that we can generate an algorithm which can be generated by us for saying, I don't know, how for each day in the simulations we loop through the different individuals and what will be the probabilities and the radius in which you need to be close to another individual in order to get actually infected, and so on. And running this, then you see that we get, again, similar type of curves, but at this time, instead of using actual mathematical equations, we generated with our own understanding of the process and environment. And because of that, we can also make them also multidimensional. For example, before we were running against just time. Now we also run them against space. And we can see the different individuals in a 2D space moving around and getting a more clear view on the simulation itself. And then if you're interested, there are also other approaches which you can use in order to make these simulations yourself. So in this case, I sort of hard-code them with myself and do it from scratch. But there are also packages in Python like Mesa, or also Hash, which is a framework which you can use in order to create the simulations, or enterprise-level tools like AnyLogic or Blender that you can use as well. And now we can quickly show you an application I developed on this, which was developed on AWS, which is using Streamlit, and has also Docker support, and is freely available on GitHub if you want to clone it, start it, or do anything with it. And yeah, so I can quickly walk through the application here. So you can see here, this is the main tab where you can get the welcoming page, and then here we can run the different simulations. And for example, this one is based on agent-based models. You can see that you have parameters for the population size, the death probability, the contact region which you need to be within in order to get infected by someone else, and for example, also the average population age, which can affect how heavy you can be affected by the disease. And then you can see that you can actually get these simulations and run them and see how the individuals move in a 2D space and how this affects the curves, which then get generated. And then you see you can get reports and different sort of analysis. And starting from this, then you can also try to test policies. For example, you can see, okay, what if now we decided that when someone gets infected, needs to immediately run to a specific location and isolate and try to not get in touch with anyone else. And in this sort of scenario, you can see that basically we can do, for example, track and tracing, and you can specify this sort of also community parameters. So for example, if the community static, if it's dynamic, for example, simulating a lockdown or no lockdown environment, and if there are different levels of communities. So, for example, if it's just a small town in the middle of nowhere, or if it's a, I don't know, 4 towns and a big center at the middle, and people moving across different towns and so on. And you can see here, then you see you get some sort of different cores with the same parameters. You can see there is this red box at the bottom, and every time that someone gets infected, immediately runs into this red box quarantine area in order to not get in touch with anything else. And you can see here, then you have different type of scenarios, like with 8 communities, 4 communities, and so on, to try to get more complexity and improve the simulation analysis the same. And apart from that, then you can see this is agent-based simulations. But coming back to mathematical models, we can also create the more advanced version of the 3 equations I showed you before. And instead of having just 3 equations, you can see you can add more states. For example, one for time-limited immunity, so people that get infected, they recover. Then for a time period, they are immune to the disease. And then after a while, they become again susceptible and can be infected again. And people that get vaccinated, for example, and don't get reinfected again, and so on. And then you can see you can play with this and get, again, same sort of simulations and create more complicated equations on top of that to make it more realistic as possible. For example, I think the imperial model that was used in the UK had more like 30 parameters or something like that. For example, these are 6, 7 parameters for a moment, just to provide a quick demo, let's say. And yeah, then there is much more on the actual presentations there. But you can feel free to explore it in your own time, because we are limited today for the time of the presentation. And yeah, so this was created from scratch using Python and using Streamlit as an interface, and Plotly for also plotting. But at the same time, you can see there are also built-in tools and libraries that are designed specifically for creating models and simulations, like this one, which is Mesa, which is shown now on the screen. And with Mesa, you can create, for example, this is a 3 forest fire simulation. So you can see that basically we got a tree that caught fire, and based on the density of the forest, you can see how this can then spread across the forest, and then how people can try to design to space out a bit the trees so that the event gets isolated and doesn't spread around constantly, let's say. And then as well, there is also a more enterprise tool, which is Hash, which provides you with built-in capabilities for visualization as well here. And in this case, you can see that you can then design more complicated graphs and these are provided out of the box, more or less, for many scenarios. So for example, there are also simulations for airport management or supply chain optimizations and things like this that people can just create and provide as template to the community for other people to use, basically. And coming back to a more recent sort of approach, we can see that basically during the last few years, there has been also the development of large language models, which have been becoming more and more popular nowadays. And this can be used also for actual simulations now. For example, during the last month alone, I've been designing different papers, like for example, this one with generative agents for human interaction, where basically we have a sort of a Sims simulation, where, as you can see in the image, you have different people basically living in different flats and interacting to each other. And each of these persons basically is a language model, and they just interact with each other, organize things, do things, and basically create a proper Sim simulations, basically. And moving forward, then there has been also other applications, like for example, language models for simulated economic agents, where basically you simulate, I don't know, language models impersonating companies and decision makers in the companies, so that they can then decide what kind of policy to apply and how the language model responds and so on. So in this case, basically you have, instead of having just one model like GDP talking with you, you have multiple models talking each other and trying to achieve greater things and narrow down the scope. And that's why, for example, also Alex Carpati, which was the head of AI at Tesla, also said that auto GDP will basically be the next frontier probably of prompt engineering, because instead of you having to get prompt really crafted to get the results, you will have 2 agents which are have an antagonist role, let's say, basically, sort of a client-customer face, approach, and they talk each other to get you then the response that you actually want in the first place, so without you being in the loop to try to get GDP to do whatever you want. And finally, also Salesforce did a nice, interesting research about it, which was based instead on reinforcement learning, in this case for the AI economist. So basically having a simulation environment where these AI models for using reinforcement learning were testing different policies, and seeing, for example, if capitalism or libertarism or other type of approaches to economy were giving better results in the long term, in the short term, and so on, to get better insights on that. And then going forward, you can see that the second paradox I wanted to introduce today is the Simpson paradox. And in this case, basically, the Simpson paradox is a phenomenon in probability and statistics where a trend that appears to appear in several different subgroups of data, but disappears or completely reverses when you look the sample in its whole completity. So, and this is really interesting because basically that means that you can get things that you completely don't expect. So, for example, in this case, you can see here that there is a simple thought experiment where we are trying to basically examine how cholesterol levels can depend on how much you exercise, basically. And here, basically, you can see that for this experiment, we decided to divide the sample into different categories, people that are under 60 and people that are over 60. And you can see that in both cases, when we see under or over 60 patients, we can see basically that as we increase the number of hours that people exercise, the cholesterol levels of the people go down. But then when we actually add the two samples together, we can see that then the correlation flipped. So instead of being negative, it becomes positive. And that's just because we consider the whole sample as a totality. And this obviously doesn't sound right to us. And there can be different reasons for this. So for example, one approach we can take is basically to try to understand if there is any sort of hidden variable which we are not accounting for in this analysis, which might be causing cause-effect relationship flips there. And therefore, it's important, for example, in this case, to consider the age, obviously, because as you increase with age, then cholesterol levels tend to naturally increase. And if you see that here, you can see that basically you get perfect correlations between under 60, over 60, and the sample together for age. And therefore, you can see basically that this was the reason why the correlation got flipped there. So in this case, going forward, let's say, you will basically do that if you perform the same analysis of the slides I showed you before, here, but you keep the age as a constant variable, then you will see instead that when you add the samples together, everything will look perfectly fine. And that's a case where the Simpson paradox can appear, let's say. And another case is the accuracy paradox. In this example, basically, we need to basically bear in mind that every time we do an analysis, we always think that going deeper will lead to better results, but that's not always the case. In fact, there might be circumstances in which having sort of the bigger picture can probably help in the long term. And that's important because you can see that basically whenever we try to create a machine learning models, we always try to optimize some form of metrics. But if we don't optimize for the right metrics, or if we over-optimize for that a simple metric, then we will just get worse results in the long term, and with the appearance of good results in the short one. And this can basically summarized as a accuracy paradox, where basically we overestimate for a sort of metric and get really good accuracy for some training or times and so on, but then in actual application is not so good. And this can be also seen, for example, when if we create a model here for here having house prices and try to predict what is a house price depending on the number of rooms. If we train a model for the Italian market and we push it to the maximum, this model will perform good for the Italian market, but then if you try to test it against the Spanish market, will probably perform much worse than a model that is less overfitted to the regional model. So if you do that simple linear regression, it probably will work well for many markets. Instead, if you do a really deep learned model, it will go well for the Italian market, but will go bad for other markets, let's say. And this can also be seen, for example, also in when you do classification type of models, especially when you have an unbalanced set of data, where we try to just optimize for either for positive or for negatives and so on, and then the model doesn't perform too well. And this can also be summarized by this quote by Charles Goddard, when he says, when a measure becomes a target, it is to be a good measure, which is really important to remember in this case. And this can also be seen also by, for example, the Pareto principle, where you see if you focus really on the 80% important things, you can always get really good results fast, instead of trying to optimize for the leftover 20% that might take ages to try actually to get, and then might not work well in other type of scenarios from the one originally planned. And another paradox I wanted to introduce quickly today is the learnability Gödel paradox. And in this case, basically, Kurt Gödel was a very important scientist of the last century, and he basically emphasized how math can have some sort of limitations, and how in some cases it can be impossible to make extrapolations about a population from a sample. And if this is the case, basically that means that any sort of machine learning or data science model will never be probably good or reliant about, and you can generate AGI, because in every case, basically, we just work on samples data. We never work on entire population of data. And this, therefore, can greatly limit our impact that we can have in the real world using just data as an input. And that's why, for example, also Giulia Perlo, other scientists, really pushing forwards to using causal AI, which is based on rules and relationship instead of just data. So to get basically same sort of results, but with much less data, make the models much less data dependent, basically. And the last one I want to cover today is the law of unintended consequences. And in this case, basically, you can see that we always strive to create really complicated models or really complicated infrastructure to get to cover any sort of edge case or anything. But this can at times make things more complicated, because that extra complexity makes more difficult then to understand when things might go wrong. And therefore, you see a domino effect that you are not really understanding what may be the source of a problem, of a bug, or anything, if the different pieces are not independent of each other and correctly connected to each other, let's say. And this can be also really important, especially nowadays with the advent of GDPR, where you have the right for explanations clause, and where people can demand to have an explanation of why some things don't work or why some decisions were made. And if you are making these sort of really complicated systems, which can be more difficult to extrapolate in design, then that makes more difficult then for you to actually provide reasoning and explanations to end users or customers, let's say. And yeah, so going on to the conclusion, basically in this presentation I provided some common paradoxes, but obviously there are way more apart from this. And this can be due, for example, some example here are the friendship paradox in network analysis, where this paradox can explain you why your friends on average have more friends than you do. And the Bergson paradox, Price paradox, Morora paradox, Birdy paradox, and so on. You can see there is a really long list. And if you have anything else that you want to add on top of this list, just let me know. I'm curious always to learn more about this. And yeah, so if you're interested in learning more about this topic, there are these 3 resources I found really useful, which is the Book of Why by Giulia Perl. Giulia Perl wrote many different type of books about causality, and the Book of Why is probably one of the most famous ones, but you are free to also explore other works that he did about this. Or also the Model Thinker, which is a more general book, and it just talks about different types of models, which nowadays are mainly associated with AI, but can be Bayesian models or any type of more historical models as well that has been ever developed during the past couple of centuries. And also thinking in system is quite interesting, where you try to connect models to each other and see how this can affect end results, for example, by cascading models or creating bigger pictures type of analysis. And that's it for me. So thank you very much. If you have any questions, just feel free to reach out.
Yes. Thank you for this very interesting and visual talk. We have some questions on Slido. If you have any more questions, feel free to add them to the Slido room in Risotto. The first question is, when you showed the plots about infections, the lines straighten out after some time. Why is this?
Which plot?
About infection, like the first plots you showed. I think it was in the online browser.
Why it goes straight after some time? Exactly. Because obviously we cover the whole population, basically. Imagine that I had a population of 500 individuals, and in fact, if you, for example, if you see here, if you add the numbers of the different lines at the tops, you'll then see that you get the maximum number of people. For example, here in this case, you have 60 people in the regional population in blue, and they go down. And then after it topped, and it becomes a straight line because obviously some people died, so that they can be moving between states, and some people got recovered, and they can't be reinfected in the simulation, basically.
So the next question is, how frequently do you experience the Simpsons paradox in your day-to-day job?
I don't mean it happened. I don't know how frequently. Like it can be in different shades, or especially because depends also the type of projects you work on. Like it's mainly when you really have to do some sort of uncrafted or clinical studies. For example, if you work in clinical studies, can be quite important to know this paradox. I see.
Great. Any more questions? You can also raise your hand if you don't want to use Slido. We have some more time left to discuss. So. All right, then. Thanks again for the great talk.
Okay, thank you.